I'd like to call for the next speaker. Mark Stone from Florida International University will represent a collaboration among FIU, UC Berkeley, on anomalous behavior of sub-10-nanometer MRAM cells.
Hello, everybody. My name is Mark Stone from Florida International University, and I'll be presenting on the anomalous properties of sub-10-nanometer magnetic tunneling junctions. So this presentation, I'll begin with an introduction, succinctly describe some of the device physics, go over the fabrication process, some preliminary results, and then conclude the discussion with a summary. So as I'm sure you're familiar with, STT-based devices have garnered considerable interest, particularly in the memory department, I guess you could say. So one of the main benefits of STT-based devices is the potential to become a universal memory due to its non-volatility and its near static power consumption.
You have to tell us what STT stands for.
Excuse me. STT is a spin transfer torque, which is a switching mechanism used to switch the magnetic domains in magnetic tunneling junctions. Now, this has been a technology that's been introduced to assist in reducing the energy required to switch magnetic domains, particularly in MRAM devices or magnetoresistive random access memories. Now, in terms of where this capability, where this could perform, we can look at this graph right here. In terms of access time and memory capacity, we propose a device that will have the speed of static RAM, the architectural density of dynamic RAM, and of course the non-volatility of flash. And of course, in order for this to become truly a universal memory, we want to push this to the right, where we can have optimal memory capacity and of course sufficiently high access time. Now, further benefits from said technology is 3D integration capability, because of certain fabrication processes, and of course its radiation hardness. Now, an STT-based device comprises of two magnetic films, one fixed and one free, separated by different coercivity, by different magnetic coercivities, and separated by a thin oxide film. Now, we would effectively switch the free layer by driving a spin polarized current through the junction. And we can define two different states, two resistive states, one parallel and anti-parallel. Parallel meaning the 0 bit or the low resistive states, and anti-parallel being higher resistance, defining a different state. So what are the main challenges being pursued in this technology? The biggest one is decreasing the switching current density, which this figure is incorrect, is in the order of megaamps per centimeter squared, and if I recall, is anywhere between 2 to 3 megaamps per centimeter squared, which is inadequately high for proper information processing. Now, another issue is, once again, we're trying to explore the physics and the sub-10-nanometer range. Obviously, there's a major fabrication challenges, and reported till date, we've encountered in reports somewhere around a cross-sectional size of roughly 10 nanometers. And scaling down these devices, we must take into account thermal stability and, of course, having sufficient on-off ratio. Now, diving into the device physics, once again, what we want to ask ourselves is, how do these devices behave in the sub-10-nanometer range? So here is a phenomenological expression that loosely describes the spin dynamics, and I want to highlight the alpha-xi ratio, which is what we want to improve on. Alpha being the magnetization damping factor, and xi being the spin transfer efficiency factor. Now, we find that when the devices are scaled extremely small, the thermal reservoirs, which are usually what absorb the spin excitations or energy excitations, become extremely small and therefore unable to absorb said energies in these magnetic domains. Furthermore, a lot of these models rely on continuous crystalline structures. We find that this is invalid because what we have instead is a more intermediate size, which is essentially a cluster of materials with finite elements. And because of such, energy exchanges between them are minimized and are much less than what we'd expect when they're in a crystal. Now, this would play a big role in reducing the damping factor because of the energy that is reduced because of required to switch these currents. Now, particular attention I want to pay is by looking at these high-level expressions right here, where we find that the relaxation time, which can effectively, if we can increase the relaxation time, we can effectively improve the coherency between the spin excitations. Now we find when we scale these devices really small, this delta G factor with respect to surface against volume, when we scale these devices small, we have more surface effects versus volume, or they become just as dominant as volume effects. And we find this delta G factor shift becomes extremely small compared to the volume. So when surface becomes dominant, we find because it's inversely proportional to this G factor shift, we can increase the relaxation time by orders of magnitude from what's current day picoseconds in large-scale device to microseconds and possibly even milliseconds. And this, of course, allows us to, improve on the stability condition, because even though with stronger coherency, we have better retention. And furthermore, when we scale these devices down, it's important to compensate with proper anisotropy energy to keep the retention. So a few more key parameters I want to highlight. It's important to utilize the proper material composition. This is a known structure that's proved to have proper out-of-plane magnetization. So it has proper out-of-plane magnetization, which improves on the spin torque efficiency factor, and of course allows us to have higher magnetization, which improves our signal-to-noise ratio when defining different states. So once again, these key parameters here directly impact the Xi, which is once again the spin efficiency factor, which facilitates the spin transfer torque effect. And by making these devices extremely small, we find that surface versus volume, surface becomes more dominant or becomes as dominant, and therefore we have an increase in relaxation time, which therefore significantly reduces the damping factor. Therefore, by improving this ratio, we can significantly drop or reduce the switching current density. Now, this is a quick overview of the fabrication process. We initially begin with microfabrication using photolithographic techniques, where we define a bottom contact here, with which we use gold, Thai gold. Then we sputter the entire magnetic tunneling junction, the entire device. We then coat the entire thing with aluminum oxide, and through ion milling, we expose the top here. And we do this on purpose to ensure there's no sidewall shortings, because of the perpendicular structure. And then we top it off with a top contact. Now, to get these to the nanoscale, we do FIB, or focus ion beam, to trim it down to the point. And we try to utilize currents that are in the order or less than 100 picoamps to minimize the destructive nature of this technique, and also minimize the doping due to the ion source. Now, over here, we have what is essentially the prototype using the FIB milling. And as we narrowed it down to a point, we did a cross-sectional analysis here where we can find the entire structure here, the tantalum, cobalt, iron, MgO, sandwiched between two contacts. Now, to verify its out-of-plane magnetization, we used FMOC, or F-focus magneto-optical Kerr effect, to verify its out-of-plane anisotropy, its out-of-plane magnetization, excuse me. And also, tantalum plays a key role, especially in the following device that I'm going to talk about, in terms of protecting the device from any oxidation and providing a really good contact, a really good contact. So over here, one innovative approach that we used to understand these devices and scale them down to such a small level was by depositing the entire junction onto a nanotip, or a nanoprobe. We essentially began, one method that we use is we begin with an STM probe, we cut it and we smooth the surface, and then we deposit the entire MTJ here. Once we do that, we further trim it again using focus ion beam, and we bring it down to a metallic substrate, such as copper, and we do our IV characteristics. Here we have found that once we did that, we have an effective switching current in the order, taking the difference between the parallel and anti-parallel states, in the order of about 100 nanoamps, which we find a switching current density to be about 0.1 megaamps per centimeter squared. Now, this has shown to be at least roughly 30 times smaller than what's been reported to date. And what else? To further exemplify the importance of the tantalum, once again, this acts as a protection barrier but allows proper contact to the metallic substrate. Now, We also applied external fields in which we shown from the phenomenological equation we can further reduce the switching currents by applying an external field. And as we did, as you can see over here, the switching current scales down with the applied field. Now here are just some more generalized IV characteristics that we find. Over here is a typical IV curve in which, as we increase the current, let's say from an anti-parallel state, we eventually switch it. We switch the free layer until they're both magnetized, and we see the quick drop in resistance there. And then we retrace it back again, and we effectively switch. We effectively go back to the anti-parallel state, defining two different regions here. The graphs aren't labeled here, but this is I versus V graph right here. Now over here is what's expected for a full magnetic loop, in which we start by saturating the entire junction, meaning both spin layers are effectively in one direction. You can define as either up and down. And as we increase the magnetic field, we eventually get to a point where one of the layers will switch due to the difference in coercivity. Will eventually switch, causing an anti-parallel state, and then we fully saturate it again. And as we retrace the step back, we see the exact same phenomena. Now, encompassing or compiling together the data that we have, one of the drawbacks from using the probe is the inability we can make the devices small, but we can't explore it bigger than the 6 to 10 nanometers that we get from the probe. So instead, we use the FIB, we prototype it using FIB, and as you can see from these larger devices, we effectively don't have much change in switching current density. But once we get past a certain threshold, there's a quick jump in which we can see that there's definitely a change in the spin dynamics, and we have a rapid change of switching current. And the same can be said as we reduce the size to the MR ratio. Even though it's not exactly large per se, at least maybe not sufficiently adequate for current day application, we do find that there is an increase, and that is related to the stronger coherence when we're dealing with this intermediate size. Now, I guess to wrap this discussion up, we find in order for this technology to be competitive in the future, we must be able to understand how it scales in the sub-10 nanometer range. Now, we chose 10 nanometers because that seems to be a threshold in semiconductors in which performance starts to become to deteriorate due to current leakage and whatnot. But we find, or at least theoretically, that as we reduce the size, we can improve on the performance of said devices. And even though right now it's in the order of femtojoules in terms of switching, there is theoretical possibility to bring it down to the attojoules, which would make it competitive for its semiconductor counterparts. Now, to reiterate the underlying physics, what we have is as we trim these devices down, we have an effect, the surface effects become just as dominant, reiterating just as dominant or even more so than the volume. Therefore, spin dynamics change radically, and as you can see, we've had in some experimental data in which we see a significant drop in the switching current. With that said, I would like to acknowledge the center for its support, and thank you very much.
Okay, go ahead, Theo.
Yes.
In the beginning you said crystallinity will play an important role, crystallinity of your structures, but then I didn't see anything about that.
Okay. Well, if you look at this graph, we assume that beyond a certain range, we can model these in terms of a crystalline structure. But once we reduce the size, we have instead we have clusters of material. And okay, I see. I further understand your question now. All right. We find that now we're dealing with more finite elements. There's other issues in terms of non-uniformity and such, because when we trim it down to a size, we have increased performance because of uniformity in this set composition. Now, when we
so you sort of assume that the crystallinity is okay, but you don't really know. To make it short, right? And because I have there's limited time, I have one more, and because surfaces, interfaces play a more dominant role, of course, when you go smaller. I would expect that would actually also lead to increased damping by more scattering of spin waves. And for you, it goes the other way around, which is great, but why is that?
Well, once again, we find that when we scale these devices, one of the key roles especially is the LS coupling. or the spin-orbit coupling. When we're at a much smaller dimension, the role that it plays with the orbit is much less. And what we have is a stronger coherence, at least according to our ab initio models, between the spin excitations. So I'm not sure I could actually argue that there is more scattering, but in fact, because of the increased coherence, we may have improved performance. And I'm not sure if I completely answered that question correctly.
It's okay.
Let's go ahead, Pedro.
Yeah, very interesting work. So the switching current depends on the thermal stability and also on the switching time. So what are those in your case?
Okay, we did effective switching times in the order of milliseconds, because we know that when we trim these devices down, there is a capability of tripping down to the super paramagnetic area. So we make sure that we do these measurements at larger timescales to ensure that we don't have any fluctuations because of such effects.
But wouldn't measuring at longer timescales make it more difficult in terms of overcoming?
No, because
if the device is not stable, then it should be more difficult to measure on a millisecond timescale than.
Well, that's correct. What we do with the larger timescales, we verify that there is still stability, rather than.
I see.
Okay, last question.
I think your most important result was that you were able to switch a magnet with 1/10 of a microamp.
Correct.
And this is at least 10 times better than anybody else has been able to do. And this, of course, is very encouraging that we can reduce the currents and reduce the energies and so forth. But why are you 10 times better than anybody else?
Once again, it boils down to some of our ab initio models. We assume that when we scale below a certain threshold, we have a completely different spin dynamics. And yes, you're right, the current is smaller, but more importantly, it's the spin current it's the current density in terms, because yeah, we can scale, in theory, there is linear scaling. As we scale down the current, we do effectively scale down, not only do we scale down the current, but we don't effectively scale down the current density. So we see as an extra order of magnitude in terms of switching energy. Not probably what, but yeah, yeah.
Okay, I think what I'd like to do at this point is thank the speaker again. And